Now for a little rational root theorem. Before we get into it, I'm just going to apologize in advance. I am sick and home right now. I will probably be coughing, but I just got to stop coughing on my iPad. Okay, so rational root theorem. It's also known as the rational zero theorem because, don't forget, roots and zeros are synonyms. They mean the exact same thing. Okay, so call it a root, call it a zero. It does not matter. Alright, well, what does this tell us? If a polynomial function written in descending order, what do I mean by that? Well, you know what descending order means. Just make sure that your exponents are going in descending order. Then any rational zero or root must be in this form, plus or minus p over q. And what are p over q? They're right here. P is a factor of the constant term, so that would be these. And then q is a factor of the leading coefficient. Okay, so you got your first and your last numbers to look at. Well, let's figure that out. P is a factor of the constant term. So what are the factors of 2? Well, we could have 2 times negative 1, or we can have negative 2 times 1. So it looks to me like it's going to be plus or minus 2 and plus or minus 1. What about the 3? Well, the 3, we have 3 times 1, and don't forget, we could also have negative 3 times negative 1. Negative, negative cancels out. So we have these right here, these are our possible q's, and these right here, these are our possible p's. Let's write them like fractions and see what we get. Okay, so let me make this smaller. And remember, these, whoops, hang on. These are your q's and these are your p's. So we got to write it in this format, plus or minus p over q. So that gives us, these are our possible rational roots. What this theorem does for us is it limits, out of the infinitely many numbers there are out there, it's going to narrow it down to a few select possible rational roots that we can then plug in. And if it's a root, guess what? It's going to make our y value equal 0. So if you take those values and plug them in, you can see which are actual roots. And then, like we talked about, we can divide them out, and we can work that polynomial down to a second degree, where we can then use the quadratic formula and find our last 2 roots. So that's how we're going to find all the roots for any polynomial function. So what do we got here? We've got, well, our p-values are plus or minus 1, so I can either have plus or minus 1 over 1. I could have plus or minus 1 over 3. I could have plus or minus 2 over 1. Or we can have plus or minus 2 over 3. Rather than writing all these pluses or minuses, feel free to do this. Plus or minus, and then I got, well, 1 over 1 is 1, then we have 1/3, 2 over 1 is 2, and then we have 2/3. Oh, I'm sorry, 2/3. Okay? So out of all the numbers in the world, we have 8 numbers to test. These 4, but plus or minus. So let's figure out which of these are real roots. Not real roots, but actual rational, I should say. Actual rational roots. Well, here's our function. And we need to plug in those numbers. So we've got, we're going to do f of 1, f of negative 1, f of 1/3, f of negative 1/3, oh, 1/3. And then we're going to do f of, what do we got? Negative 1/3, and I got f of 2, and f of negative 2. And f of 2/3, and f of negative 2/3. Those are our choices. Okay, I copy everything down, right? 1, negative 1, 1/3, negative 1/3, 2, negative 2, 2/3, negative 2/3. Let's move on. Okay, so in the interest of time, we can all plug these into the calculators, but these are going to be the responses you get. If you plug in x is 1, you get a y value of 1. Plug in negative 1, you get a y value of negative 0.777777, etc., etc. Nope, that's incorrect. I'm sorry, that is the value for positive 1/3. If you plug in 1/3, you get negative 0.77, etc., etc. When you plug in negative 1, you get negative 15. If you plug in negative 1/3, you get negative 4.33333, etc. You plug in x equals 2, you get a y value of 12. Plug in negative 2, you get a y value of negative 56. plug in 2/3, you get a y value of 0. And if you plug in negative 2/3, you get a value of negative 8.444444, etc. Guess what? We just found ourselves a root. 2/3 is a root. Now, we could take that and take it to the next level, but we're going to wait for that. We're going to divide that out, and then we can get this down to an x squared. And once we get it down to an x squared, we could use a quadratic formula or factor it nicely and find all the roots. Alright, before I assume anything here, which you know what happens when you assume, let's talk about the number system real quick. That is our complex number. Looks like the C from the champion sweatshirt. C stands for complex number. Of complex, that is every number known to us to this point. Anything that I say is a complex number. Of those, you can have real numbers, or you can have imaginary numbers. And that's a complex number. And then of the reals, you can have rational numbers, okay? Or you can have irrational numbers, but they're all real numbers. And then we break down rationals even further. That's when we start talking about, what do we got? Integers. Just going to write integers and so on and so forth. We've got whole numbers and natural numbers, but this is what we have to focus on, okay? Copy this down, please, if you're not sure about it. Pause it if you need to. For those in second period, you were already introduced to this fine, dapper gentleman here. For everyone else, his name is René Descartes, and I love that picture of him. This is what he actually looks like. Pretty darn close, huh? I like it. Well, anyway, he's responsible for a lot of things in math. One of them being this, the rule of signs. And what it does for us is it tells us the maximum number of real roots a polynomial function is going to have. Notice here that it says maximum number of. It doesn't give us the value themselves, but rather it gives us a quantity. I know I'm going to have one real root. I'm going to have 4 real roots. It tells us how many real roots we're going to have. And then from there, I can figure out how many complex roots there are. Okay. Remember, if we're given something like this, where I have an x to the 4th polynomial, and I know with certainty that 2 of them are real, well, then that means since I have to have 4 complex roots, 2 of them will have to be imaginary. And it gives me guidance what I'm looking for. Okay? Unlike long division and synthetic division, actually, I only have long division, but we have to ignore the 0 coefficients. Okay? If we don't have an x to the 3rd, just leave it out. We don't put a 0x to the 3rd. Okay? Great. Alright, so let me clean some of this up here. And here is his rule. Okay, right there. The possible number of positive real zeros. Okay, so it breaks it down into whether they're positive reals or negative reals. The way we figure out the number of positive real zeros is it's the number of changes in sign of the terms of our function f of x, or less than that by an even number, namely 2. All right, and I'll show you what we mean by that. How do we find the negatives? Well, the possible negative real zeros is going to be the number of changes in the sign of terms of f of negative x. If we were to switch the x in our function to negative x and then count the sign changes, it's either going to be that number or less than that number by an even number, namely 2. Okay? It always comes in pairs. So let's do a problem and figure this out. If you need to pause this to copy it, do what you got to do. And so here is our lovely example. We are gonna find the number of real zeros of this function. Okay, so here it is. We have f of x. Well, you can read it. So get that in your notes, and then we're gonna do the rule of signs here. So the f of x, what we're doing is we're counting the sign changes. Remember, if you don't see a sign in the beginning there, it's just assumed to be positive, obviously. So let's count the sign changes. Again, it has to be in this order. It has to go in descending order based on the exponents. Okay? So we go from plus to minus. That's one sign change. We go from minus to plus. That's another sign change. We go from plus to plus. That does not change signs. We go from plus to minus. That does change signs. We have 3 sign changes. and then it goes from negative to positive again. That is a fourth sign change. The signs have changed 4 times, which means I could tell you with certainty that we are either going to have 4 real positive zeros, or 2 real positive zeros, or 0 real positive zeros. Okay, again, it's the number of sign changes or less than that by 2. I said even number, I should just say 2. All right, let's do the negatives now. So the negative is if I put in a negative x. So what is that? F of negative x. It's easy to remember. The positives are a positive x, the negatives are a negative x. Well, think about that. I'm going to plug in a negative x everywhere I see an x. Oh, I'm sorry, that's a negative x to the 4th. Plus 3, and then we got a negative x to the 3rd, and then we got a plus 9, we got a negative x that we're going to square, and then we got a negative x, and I'm going to stick in my little plus 5, right? That's a 5 right there, okay? Boom. Plus 5. Okay. Let's see what this simplifies down to. We have f of negative x equals this. Well, think about this. Whenever you have a negative, odd bunch of negatives, well, you're always going to have one left over. Negative, negative makes it positive. Negative, negative makes it positive. We still have another negative left over, so that makes it negative, x to the 5th. Now over here, minus. We have a negative x times a negative x, then a negative x times a negative x. When you have an even bunch of negatives, it becomes positive. So it's just going to stay x to the 4th, but because it was negative here, it's going to still be negative. Over here, we have a negative x times a negative x times a negative x. That makes it negative x to the 3rd, which is going to make this term negative 3x to the 3rd. Here, we have a negative x times a negative x, which stays positive x squared. So we have positive 9x squared. Negative, negative makes that a positive x, and we have a positive 5. Okay, let's count our sign changes. Negative to negative, nope. Negative to negative, nope. Negative to positive, yes, we have one sign change. Positive to positive, nope. Positive to positive, nope. Positive to positive, nope. We have one sign change. That means I'm guaranteed to have one negative real root. Now, because you count down by 2's, if I count down by 2's here, I'd be at negative. Since that is impossible, you can't have a negative quantity. You either have real zeros or you have no real zeros. Once you hit 0, you just stop. You can't have less than 0 roots. Okay? So the final answer here is we have 4 or 2 or 0 positive real roots, and we have definitely 1 negative real root. Okay, let's tie it all together now. We are going to determine the number of complex roots, the number of real roots, the possible rational roots, and the actual rational roots. Everything we just went over. And we're going to do it for this function right here. We have a polynomial, a 4th degree polynomial. Alright, well the first one should be easy if you remember. The number of complex roots, whatever the highest degree is of your function, in this case it is a 4, that means we are guaranteed to have 4 complex roots. Okay? They may be real, they may be imaginary, but we have 4 of them. Well, of those complex roots, let's see how many are real. Well, how do we figure out how many are real? We're going to use Descartes' rule of signs. Alright, so the way we find the positive real roots is this. We count the sign changes of our function. Here's our regular function. So, positive to positive. Here's one sign change. Nope. Yes, we have 2 sign changes, which means the number of positive real roots are either 2 of them or 0 of them. Okay, remember when you get to 0, you stop. You can't have a negative quantity of roots. That's the notation for the positive reals. For the negative reals, we take f of negative x. All we do is we substitute it at negative x, a negative x, a negative x, and a negative x, and we see what happens. Whenever you have an even exponent, it stays the same sign, and when you have an odd exponent, it changes the sign. Okay, we talked about that just before. So let's count the sign changes. We go from positive. There's one sign change. Nope. Yes, we have 2 sign changes. Nope. For the negative reals, we have either 2 of them or 0 of them. Remember, they come in pairs. And so, what's next? The possible rational roots. Well, let's figure out the possible rational roots. We're going to use the rational root theorem. And if we do so, let's see what we got here. Let me change this to yellow. So we have, remember, here's our function up here. So let me just look it up here. That's a 1 in front there, and that's an 8. Which means, if you remember the rule, these are p's over q's. We're either going to have 1 over, what am I got over here? Oh my goodness gracious. Okay, I'm back. Let's do this again. We have, this is an 8, so these factors are either going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And then the q, which is the denominator here, well, the only factors of 1 are plus or minus 1. Could be 1 times 1 or negative 1 times negative 1. Which means our denominator here is all 1. So that's why what you're looking at right here is the only rational roots we have to figure out. We have 8 of them. Okay? So there, possible rational roots, 8. Well, that's not really easy to see. How about 8? Okay, now of those possible rational roots, how many are actual rational roots? Well, what we want to do there is we're going to take our f of x here, and we need to figure out what is f of 1, what is f of negative 1, what is f of 2, what is f of negative 2, what is f of 4, what is f of negative 4, and of course, let's not forget about 8 and negative 8. The easiest way to do this when you have so many to plug in, go into your y equals and plug it in, and then just find out at these specific x values what's your y value. Depending on what calculator you're using, it'll be a little different, but it's pretty straightforward to find out. So in the interest of time, I've already plugged all these in, as you can expect. And let's see, what came out to be the real roots? We have 4 of them. Of all of these, we have 4 of them. Okay, so this one is a root. And what else we got? We got 2 as a root. This is a root. And both of the 1s, negative 1 and 1, are both roots. Okay, so we have 4 rational roots. Okay, we know with certainty that 1 and negative 1 are a root, 2 is a root, and negative 4 is a root. Now, yay, we got the answer. We've answered all these problems. The actual rational roots are 1, negative 1, 2, and negative 4. But the bigger picture, though, think about what we just did. We took a polynomial. We took a 4th degree polynomial, and out of the blue, we figured out all the roots for it. Ain't that pretty cool? Well, also think about this. Say we only found 2 of them here. Okay. Well, if we found 2 of them here, not 4, we found 4 here, which coincides to what we just found over here. All right. We just found 4, which means with certainty we just found 2 real roots and 2 negative real roots, because rational roots are real roots. So negative 1 and negative 4 are our 2 negative roots, and then positive 1 and positive 2 are our 2 positive real roots. Right on the money there, buddy. Thank you, Descartes. But say we only found 2 of them here. Well, we could easily find the other 2 by taking that 4th degree and dividing it out. Don't forget that when you divide out, think about it even like this. This is something we've learned in basic algebra, right? If you have an x to the 4th term and you're dividing out 2 x's, or an x squared if you will, that is going to bring your function down to an x squared. And like I said before, once we have it down to an x squared, the rest of it's easy. Plug it into the quadratic formula, factor it nicely, whatever works out, and there are the final roots. Everyone, I'd like you to get this in your notes, so when you get into class, you can just open up your notebook and know what we're going to work on. What did we do here? Rational root theorem, so we're going to be working on page 206 in class tomorrow. See you then.